So what is electron affinity? Well, in my last lesson, I talked about ionization energy, which is the quantity of energy required to remove an electron from a gaseous atom in its ground state. And electron affinity is almost the opposite of that. So we're basically going to take a gaseous atom, and now we're going to add an electron to it. And the idea is how much energy is released when this atom captures that electron to become an anion, okay? Now, the enthalpy change for, let's say, fluorine in general is going to be negative because that energy is being released. We're taking a negatively charged particle, an electron, and we're bringing it closer to an atom with an effective nuclear charge that's positive, right? And so the electron is attracted to this atom, to the nucleus. And so when we're bringing these two oppositely charged attracted particles together, we're releasing energy. But the electron affinity is just going to be the positive value of this. So if there's a positive electron affinity, that means that the enthalpy for that reaction was negative and that energy is being released. So what's the periodic trend? So we know from my last video, when I talked about the ionization energy, that increases up and to the right because as we go up and to the right, the nuclear charge or the effective nuclear charge increases and atomic radius decreases, right? So as the atoms get smaller, the electrons in the valence shell are closer to the nucleus, and so they are more attracted to that positively charged nucleus. And so it takes more energy to remove an electron from those atoms. And then we could just think about it like that. Okay, if an atom, it takes a lot of energy to rip an electron away from it, well, then the opposite is going to be true as well, in general, that is going to release more energy when it gets an electron, right? So in other words, if an element down over here, like francium, it takes very little energy just to pluck an electron off, that doesn't show that it's really attracted to some new electron very much, right? But an element like fluorine, well, it has a very high ionization energy. It takes a lot of energy to rip an electron away from it. So that would indicate that there may be more energy released when it receives one, okay? So in general, electron affinity increases up and to the right as atomic radius gets smaller and as ionization energy increases. But there are exceptions, right? And so I'm not going to hit every exception. I'm just going to talk about the general things that happen here. And there's two major exceptions that you need to be aware of that will help you on questions like, hey, rank these elements that are in maybe the same period according to increasing ionization energy. If it's in a group, it's going to be much easier. In general, in a group, it increases as you go up, okay? They all have essentially the same electron configuration. Maybe something in period 2 doesn't have a D sublevel in shell 2, whereas something in period 3 might. But let's not focus too much on that. In general, I just lost my cap here. In general, it's going to increase as you go up a group. But when we're looking at the periodic table, there's two locations, two groups that are going to stand out. And it's group 2A and group 5A. And so if we look at, let's take a look at group 2A. Let's look at like beryllium, for example. If we have beryllium, we have, and I think I used this in my last video too, we have 2 protons in the nucleus, and there are going to be 2 electrons in the valence shell, right? And so that's because it has the 2s2. And let me just pull up my actual periodic table here. Here's beryllium, it's number 4. Let's just do this. There's 2 electrons down here in the 1s, and then the 2s is full. Now, in an atom with only 1 electron, like hydrogen, the different energy levels, the sublevels have the same amount of energy. So if there's only 1 electron, the 2s and the 2p have the same energy, and the 3s, the 3p, and the 3d have the same energy. But in multi-electron atoms, that is not true. And that's why when we do electron configurations, we fill them up in the order that we do, because the different sublevels in multi-electron atoms have different energies associated with them. And so I did talk about that in that lesson, but let's get into that just a little bit more right now. The idea is that the 2p sublevel is higher energy than the 2s. So if we looked at like the energy, right? It's like the 1s is going to be low energy. Then there's the 2s here. And then the 2p is going to be like over there-ish. And then let's just say that the 3s is here. This is not to scale, but the idea is that the 2p is higher energy than the 2s, okay? So if we look at beryllium, shell 1 is full. It's just the 1s is shell 1, so 1s2, we're done. 2s is full. Now, in order to get into the 2p electrons are, on average, further away from the nucleus, and it's a higher energy sublevel. And so if we just want to simplify this and do just a little bit of hand waving here and use the planetary model that we're doing here, the 2p would kind of be like this, right? It's like it's on the exterior. And so if we have, I think I'm missing 2 protons for beryllium here. There's 4 protons here, right? It's number 4. And so if we look at it from the perspective of this planetary model, if we wanted to add another electron here, well, what is that seeing? It's seeing this inner region of the 2s and the 1s canceling out the nuclear charge. If there's 4 positives in the nucleus, there's already 4 negatives from the 4 electrons closer than the energy level or the sublevel rather, that the new electron is going to jump into. And so the effective nuclear charge is essentially 0, right? And now you'd have to put this electron into a new sublevel that is higher energy, and we'd have to start filling up the 2p. So in other words, group 2a, they have a lower electron affinity than group 1a. And so, as I said earlier, in general, electron affinity increases up and to the right. So as we go across the period, you would expect each next group has a higher electron affinity, but that's not true for group 2a. We have whatever energy this element is, and then we get to the next one, and it goes down. In the case of beryllium, it's like 0 or negative. Now, we get to the next element. We have another proton here. So now we're increasing the nuclear charge, and now we have an effective nuclear charge that's about +1-ish, right? So now this element, boron, is going to be happy to accept that next electron, which would be like over here in this instance, right? And so there is going to be, we're going to go back to having a positive electron affinity or a non-zero or just a higher electron affinity as we go to the right again. Now our next exception is going to happen at group 5a. And so if we look at group 5a, that's where nitrogen is, right? So let me just put beryllium here. That was 2a. Let's fix this. That looked bad. Okay. So in group 5a, we have the P3, whatever the N is, whatever the shell is, we have P3. And what does the P3 look like? Well, in a P sublevels have 3 orbitals, right? So let's draw that out. Let's just say we're doing nitrogen right now, and this is the 2p. There's 3 orbitals, and it's going to be 2p3 because nitrogen is in the first, second, third position in the P subblock. Again, if you don't know how to do this, look at my electron configuration and my orbital diagram videos. That'll teach you how to do what I'm talking about right now. But in the 2p, nitrogen has 3 electrons, and each of them get their own orbital, right? So they're all going to spin the same direction, and they're all going to be in their own orbital. Now, what would happen if nitrogen was trying to accept another electron, right? So if we tried to force an electron on nitrogen, is it going to be attracted to it, or is the electron going to be captured by the nitrogen? And the thing is, we have 3 electrons, each in their own orbitals. So we have this symmetric charge distribution, and we're minimizing like the Coulomb repulsion, right? Because the electrons all have their own space, and they are not going to be repelling against each other so much. There's also a special stability from the electrons all facing in the same direction when you have a half-filled sublevel, and that is kind of it's a quantum mechanical phenomenon, exchange energy. I can talk about that in another lesson if you guys want. Comment down below if you want me to get into that, but we can hand wave for now and just say that there's a special quantum mechanical lower energy that you experience when the P levels, or like the D levels even, are half filled. So in group 5A, all of those elements have a half-filled P sublevel, right? They're all in the third position of the P subblock, or the P block. And so adding another electron, one, we're going to experience repulsion, and then two, we're going to be messing up that special lower energy due to the quantum mechanical effects, and our charge distribution is going to be asymmetrical now. And so basically, this is not favorable. And in the case of nitrogen itself, the first element that we see that has a P3 orbital diagram, that's actually going to be a 0 or less than 0 rather, electron affinity. It does not want that electron. But then as we go past it, once we get over to oxygen, now we're adding another proton to the nucleus. So we've kind of already messed up the orbital diagram here. We've already messed up this perfectly half-filled sublevel. And so basically, once we get to oxygen, we're increasing the nuclear charge. We've already kind of gotten over this hurdle, and now we're going to continue on with the regular trend of electron affinity, increasing up and to the right. And then if we look at the noble gases, in general, they have a near zero or negative electron affinity because their valence shell is completely filled. And in order to put another electron in, it's going to be similar to the case that we saw in group 2A. We'd have to jump up to a higher energy level, except it's even more severe. Because in the case of beryllium or any 2A element, the next electron is jumping up into the same energy level, but the P. And the P is just a little higher energy than the S in the same energy level. But when we go to a noble gas, now we have to jump up to the next energy level, right? So if I'm looking at neon and I want to see if it'll take an electron, and if it's going to release energy, if it's going to do that, now I have to put that next electron in the 3s. And that's way higher energy than the energy level of 2. And so it's not going to want to do that. It's going to be 0 or less than 0. And so in general, the noble gases have very low or negative electron affinities. And then again, group 2A is going to be lower than group 1A, and group 5A is going to be lower than group 4A, okay? So I have a little graph here so you can take a look at what the trends look like. So just know that in general, electron affinity increases up and to the right, but there are exceptions, especially the ones that you should know about are in group 2A and 5A. And one last thing that I want to mention is how do we actually figure out what electron affinities are, or how do we measure them? Before I do, guys, if these lessons help you guys, please give a like, follow, share, save this so you can review it again later, and check me out over here. If you patronize me, that helps me to continue making these videos for free. So how do we actually experimentally get the electron affinities? I'm not going to go into too much detail, but what I want you to know is we actually do this reaction in reverse. We take the negatively charged species, right, this anion, and we remove the electron from it and see how much energy is required, or how much energy is released, or if there's no energy required at all, right? And so electron affinity is measured in reverse of the reaction that we write out for its definition. All right, guys? So again, thanks for watching, and I'll see you in the next one.